We now move on to the third part of the chapter, and that is flotation. So, in fact, I would say the flotation part was already done by us partially when we saw the upthrust part. So, in the upthrust part, we understood that flotation bhi kaise hota, that is, if I have got a body and that the weight of the body, if it is greater than the upthrust, then it is going to sink. When it is going to be less than the upthrust or equal to upthrust, it is going to float. So the same thing is going to be in detail now in the part of flotation. So first of all, let us understand the principle of flotation, and over here we also have certain important applications of flotations which are very important for give reason part of the point of view. Principle of flotation. When we read that when a body, we have already read that when a body is immersed in liquid, the following two forces act on it. The weight W of the body acting vertically downwards through the center of gravity G of the body. This force has a tendency to sink the body. Second, the upthrust FB of the liquid acting vertically upwards through the center of the buoyancy B, that is the center of gravity of the displaced liquid. The upthrust or buoyant force is equal in magnitude to the weight of the liquid displaced. This force has a tendency to make the body float. So figure shows the two forces W and FB acting on a body floating in a liquid, on a liquid. So we have got over here, if this is a container, and in this container there is water filled up to this particular point, and you have got a body which is of this particular dimension, partially inside the water and partially above water. The center of this particular thing, that is this particular point, is G, the center of gravity, and through this particular point is the weight of the body which is acting downwards. Okay, and the center of the buoyant area, that means the center from over here, इसके और इसके बीच में, यानी यहाँ पे, is a force which acting upwards, which is FB. This point is buoyant point of the center of buoyancy, that is B. So G acting downwards, B acting at G, the W acting downwards, and at B the FB acting upwards. So in magnitude we see that W is equal to volume of solid into density of solid into G. Okay, weight of the body is nothing but mass so it is nothing but M into G. Mass is nothing but volume into density, so volume of solid into density of solid into G, that is W. Whereas FB, we know the formula as V, volume of the liquid displaced, volume of the density of the liquid, into G. Or we can say the volume over here. So we can take volume, this is the complete volume of the body, where this is the submerged volume of the body. So Vs, we'll take it as the volume of the submerged part of the body. Okay, or we can call it as small v. So we can say it as small v. This is capital V, that is the complete volume of the body, where small v rho Lg will be the FB, that is the volume which is the submerged part of the body. The submerged part of the body will be small v. Obviously, the upthrust FB is maximum is equal to F dash B when the body is completely immersed in the liquid. So depending upon whether the maximum upthrust FB is less than, equal to or greater than the W, the body will either sink or float in liquid. So we consider the following three cases. So W is greater than FB1. So it is first case is W is greater than F dash B. That is nothing but the maximum upthrust when the body is completely submerged in water. When the body is completely submerged in the liquid, the upthrust what we are getting is the maximum upthrust, and that is F dash B. So if W is greater than F dash B, then the body is going to sink. Okay, it is going to sink. So weight of the body is greater than the weight of the displaced liquid. In this case, the body will sink as shown in the figure. The apparent weight of W of the body, that the weight of the body inside the liquid, as measured by spring balance, if it is attached to the body, will be W minus FB acting vertically downwards. This is the case when the density rho of the solid is greater than the density L of the liquid. So what are the things over here? First thing is that apparent weight will be, in this case, will be equal to W minus FB, F dash B, and another thing is that rho of the solid will be greater than rho of the liquid. Density of the solid will be greater than the density of the liquid. This is the conditions what take place when the body is going to sink. So when the body sinks, first condition will be the weight of the body will be greater than the maximum upthrust. The second condition will be that the apparent weight of the body will be equal to weight of the body in air minus upthrust. And the third thing will be the density of that particular body will be greater than the density of the liquid. And that is why it sinks. The second condition what we are having over here is the condition where W is equal to F dash B. So if W is equal to F dash B, the weight of the body is equal to the weight of the displaced liquid. In this case, the body is going to float. So it will float in such a way that the complete body is completely immersed in water. So it is going to float with completely submerged in water. So body will be completely submerged in, so body completely submerged in water. And here the apparent weight will be equal to, what is W minus FB? Both are equal, so it will be 0. Apparent weight will be 0. So the apparent weight will be 0, the density will also be same. So we have that rho S will be equal to rho L. This is the condition for W is equals to F dash B. If W, that the weight of the body, is equal to F dash B, that is maximum upthrust, then the apparent weight will be 0, the body will be completely submerged in water, and rho S will be equal to rho L. We see the third case and the final case over here, that is W is less than F dash B. Again the body is going to float. Now the body will not be completely in water, it is partially inside water and partially above water. And the FB which is going to be given out, that will not be maximum, it will be just sufficient enough that it is equal to W. So in this case, FB will be equal to W. That means while floating, the upthrust what is being given by the submerged part of the body, upthrust given by the submerged part of the body will be equal to the weight of the liquid. So volume of the submerged part of the body will be equal to the volume of the FB due to the volume which is submerged part of the body is equal to the weight of the solid. So in this case, the weight of the body is less than the weight of the liquid displaced by it when it is held completely immersed in the water. In this case, the body floats partially above and partially below the surface of liquid as shown. Only that much portion of the water body gets submerged, by which the weight of the displaced liquid becomes equal to the weight of the body. Okay, so weight of the displaced liquid equal to the weight of the body जब ये होता है, उतना ही पानी बाहर निकलेगा, उतना ही body submerge होगा, उतना ही water displace होगा, right? So it is only that much portion of the body gets immersed, only that much portion of the body is going to get immersed such that the submerged will be only that much portion of the body will get submerged, by which the weight of the displaced liquid, the weight of this displaced liquid will be equal to the weight of the body. In this situation, by floating with weight Wx on the center of gravity of the body, while upthrust Fb x on the center of buoyancy P, which is vertically below G. So this is what I shown you. This is G and B is vertically below G, and that is B is the center of buoyancy, G is the center of gravity. Buoyancy B, which is vertically below G, and the weight W is equal to upthrust FB only due to the submerged part of the body. Thus, the apparent weight of the body will be 0 in this case also. So here also it is going to be happening that apparent weight is equals to 0 and rho S will be less than rho L. The apparent weight of the body will be 0 in this case also. The density rho of such a body is less than the density L of liquid, that is rho is less than rho L. From the above discussion we find for a floating body, weight of body is equals to weight of liquid displaced by the submerged part of the body, or W is equals to FB. So yes, that is what is the most important part, that for a floating body the W is equals to upthrust. The weight of the body is equals to the upthrust, or weight of the body is equals to weight of the liquid displaced by the body. Okay, so that is nothing but the and the apparent weight will be 0. So we have the principle of flotation, that according to principle of flotation, the weight of the floating body is equal to the weight of the liquid displaced by its submerged part. Okay. What is the principle of flotation? That weight of the body will be equal to the weight of the liquid displaced by the submerged part of the body. Okay, weight of the liquid displaced by its submerged part. Okay, that is nothing but the principle of flotation. So with the principle of flotation, we can easily make a particular formula now. So relationship between volume of the submerged part of the floating body and the densities of the liquids and the body. So we have over here what we have over here is we have the weight of the body, W is equals to V, that is capital V, that is volume of the body, into density of the solid into G. Okay, or if you want to make it more clearer, we'll write over here this way: weight of body W is equals to M mass into G. Mass is equals to volume into density. So therefore W is equals to volume V into density rho S into G. This is W. We then know that weight of the liquid displaced, weight of liquid displaced is equals to FB, and FB is equals to V, that is small v into rho L G, where small v is volume of submerged part. Okay, the volume of the submerged part is small v, so that's why it is FB is equals to V rho L G. But we know that while floating, W is equals to FB. So what is W? V rho S G is equals to small v rho L G. G can cancel. So rho small rho S upon rho L. So it is rho S upon rho L is equals to small v upon big V. That is the formula for principle of flotation, that volume, the ratio of the volume of the submerged part of the body to the volume of the body is equals to ratio of the density of the solid upon ratio of density upon liquid. So that is volume of immersed part of the body upon total volume of the body is equals to density of body upon density of liquid. So cork of density rho S is 3 upon 4 gram per centimeter cube. While floating in water will have its 3/4 part immersed inside water because rho L is 1. and 1/4 part outside surface of water. So when you know that the rho density is 3 upon 4, that means that 3 upon 4th part of that particular rho s upon rho l. So when we are talking about water, then we know that rho l is 1. So 3 upon 4. So volume of submerged upon volume of the body is, if it is 3 upon 4, that means submerged part will be 3 and 1/4 part will be above the water. So that is what we understand from this particular kind of formula. Also we know that when a cube of ice of density 0.9 will have 90% of the volume of its body inside the water, and only 10% will be above the water. So while 10% outside the surface of water. So that's how we can see that how the cubes of water when we add cube of water into the cubes of cubes of ice in the water, you'll find they float in such a way that 90% of the ice is inside water and 10% is above the water. Okay. Now we see certain applications of the principle of flotation, what we can see in our normal life. Okay, so that's the principle of flotation applications. Now, first is flotation of iron ship. An iron nail sinks in water while a ship floats. You can see iron nail. Okay, a nail, if I put in water, will it float? No, it sinks. Whereas a ship, which is such a huge body, it floats. Why is that so? Because the ship is made that way. It is constructed that way that it has so huge a volume, because there is air in between. So there is a huge volume. So its mass to volume ratio, that is the density, is less than that of water, and hence it is able to float. So if you place an iron nail on the surface of water, it sinks. This is because the density of iron is greater than that of water. So the weight of the nail is more than the upthrust of the water on it. On the other hand, ship also made of iron, but they do not sink. This is because the ship is hollow and the empty space in it contains air, which makes its volume large and average density less than that of water. Therefore, even a small portion of the ship submerged in water, the weight of the water displaced by the submerged part of the liquid ship becomes equal to the total weight of the ship, and therefore it floats. Okay, so it's made so huge even from the bottom that when it is going to be inside the water, at that time, due to the amount, that is the water displaced, weight of the water displaced by that particular huge volume will be so high that it is equal to the weight of the whole ship, and that is the reason it is going to be floating. So that's why a ship which is so huge floats, because it is made that way, it is made hollow, whereas the iron nail sinks. A very important question in give reason. Second, a loaded ship is submerged more while an unloaded ship is less submerged. Of course, when the loaded ship is there, the total mass W of the ship will be more, and because the total weight is more, that's why it will need more of its volume to go downwards inside the water. So it will be requiring more amount of submerged part of the body, and hence it is going to sink a bit more, or it is going to be submerged more inside water. When cargo is loaded on a sailing ship, its weight increases. So it sinks further to displace more water till the weight of the water displaced by its submerged part becomes equal to the weight of the loaded ship. If cargo is unloaded, the ship will rise in water till the weight of the water displaced balances the weight of the unloaded ship. That's why if you load the ship, it goes down. When you unload the ship, it goes up. So this is the movement of the water of the ship, or when it is loaded or unloaded. The ship begins to submerge more as it sails from seawater to river water. Now this is very easy, because we know that the sea water has got a density which is greater than the river water. More the density, more the upthrust. More the upthrust, that means lesser submerged part. Hence, it is going to be sinking more in the river water as compared to the submerged more in the river water than compared to the sea water. Water of river is of low density than that of sea, and the density of water of different seas is also different. Therefore, when a ship sails from a sea of water of higher density to a sea of water lower density, or from a sea to a river water, it sinks further. The reason is that according to the law of flotation, to balance the weight of the ship, a greater volume of water is required to displace its water of lower density in river or sea. So if you are taking river or sea of a lower density, then because the weight of the body of the ship would require more amount of water to be displaced because the density of the liquid is less. So because of a lesser density, the weight of the liquid displaced will be less. Accordingly, to compensate with that particular loss in the weight of the liquid because of the density, you will have to add some more. It will require more amount of water to be displaced, and it will sink a bit more than in seawater. And then there is something which is called as a plimsoll line. Now this is very important. See, all the ships, if you see, on the front part and on the back part, in certain areas of that particular ships. So if this is a ship over here like this, if this is a ship, there will be lines like this, like this, like this. Okay, there will be lines over here. So maybe 2 lines, sometimes more than 2 lines, even more lines. But these lines which are here are called as plimsoll line. This is the line which tells you that whether it could see when the water level goes above this or up to this, they will stop loading the ship, because the moment the water goes above this, then there are chances that this boat will sink if there is a change in density on their pathway. Similarly, if the water level goes below this, then there is a possibility that the ship which is like this may topple down like this, because वो इतना ऊपर आ जाएगा कि वो उसको balance ही नहीं रहेगा and it will fall on one side. So that's why they need to at least bring the water level up to this point, and for that they will even add some sand or something in the boat, in the ship, so that it weight is, so if it is completely unloaded, so just to make it loaded, they may put some stones and bags of sand so that the weight of the ship increases, so it will go below the plimsoll line. So each ship has a white line painted on its side, known as plimsoll line. This line indicates a safe limit of load for loading of the ship in water of density 10⁻³ kg per meter cube. So when the water is density 1 or 1 RD, relative density 1, at that time this is the safe limit for the ship, that it will not sink. Okay, a ship is not allowed to be loaded further when this plimsoll line starts touching the water level, so that when it sails in seawater of density more than 10⁻³ kg per meter cube, only the part of it below the plimsoll line remains submerged in water. An unloaded ship is filled with sand and at its bottom. An unloaded ship floats with its very small volume inside water. As a result, its center of gravity is higher and its equilibrium is unstable. So the center of gravity of this particular ship should be somewhere here, so it is within the water, then it's not a problem. But if the center of gravity is over here and the water, if the center of gravity is up to this point and the water is up to this point, then there is a possibility that it will be unstable and there won't be equilibrium. There is a danger that it may get blown over by its sides by strong winds. Therefore, an unloaded ship is filled with sand or stones called ballast at its bottom. This lowers the center of gravity to make its equilibrium stable. So, of course, I gave you to this line, but this line may not be required. You just have the plimsoll line is only this one, but you have to see to it that it is not being kept completely unloaded, because if it is unloaded, then there is a possibility of the center of gravity becoming higher, and when it happens, then there is a possibility that due to strong winds or strong water currents, it may topple out, or it may not be balanced, or equilibrium may not be there. So that is the reason what they do is they are going to fill the lower part of this particular ship with sand or stones, so that it is, which are called as ballast, which will increase the weight over here and lower the center of gravity, and hence it is going to keep the equilibrium of the ship inside water. Flotation of human being. The average density of human body depends on the proportion of its constituent like bones, blood, muscles and fat in him, as each constituent are different density. Further, it also depends on the amount of air in his lungs at that time. The average density of body with empty lungs is 1.07 grams per centimeter cube, while with lungs filled with air is 1.00 gram per centimeter cube. A good swimmer can float on water like a floating object, with his lungs filled with air and nose and mouth projecting just above the water surface. The weight of the water displaced by him is then nearly equal to his own weight, thus he can swim with a very little effort. See, when a body is able to float, when a person is able to float, it means that his density is equal to the density of the water, or maybe even less than water. Normally it won't be less than water, but at least it will be equal to water. For such a condition, it is required that the lungs, what we are having, they are completely filled with air. So we are taking a deep breath and we are quite calm. So when the lungs are filled with air, the volume of the body expands or increases, and that gives us the density of the body to be 1 gram per centimeter cube, which is same as that of water. And that's the reason the person is able to float easily on water, and at the same time he is able to swim easily because he is floating and because he is having his lungs filled with air. But if your lungs are not filled with air, then the density of the body becomes 1.07. That means it is greater than water, and hence the person may sink. Okay, that is precisely what happens when a person is drowning. When the person is drowning, at that time he is so much zapped, or he is so much scared, that he is not able to breathe, and that's why his lungs are empty, and hence his density increases. If the person would just relax, then automatically he will be able to breathe properly, and if he breathes properly, then his lungs will be filled with air and he will be able to expand. That means he will be able to have a density almost equal to water, and his chances of drowning will be less. But what happens, जैसे भी कोई डूबेगा तो ऐसा होने लगता है, तो वो जब भी हुआ तो क्या हुआ, we are not able to breathe. Okay, we don't breathe, and because we don't breathe, that's why we sink inside the water. So those who know swimming, they will not be scared that okay, I'm falling, I'm beyond from a great height, they fall into the water, and then what happens? Are they scared? No, they're just going to keep calmly come upwards. You'll just swim upwards. They'll just easily come upwards. In fact, when they fall down, अपने आप ऊपर आते हैं. They don't require a push to go it upwards. अपने आप they will come outside. Why? Because their lungs are filled with air, and that's why they are able to float on the body, on the water. So because they are able to float on the water, then automatically the body rises upwards. So that is how we see that if you are having a lungs completely filled with air properly, then we are able to float much better as compared to the empty lungs. And hence it is also easier to swim in a sea water than in a river water or a pond, because sea water the density is more, because the sea water density is 1.02, and so there are chances that the body will at least, अगर थोड़ा भी breathing का problem हुआ तो भी 1.02 तक तो आ सकता है. So that's why the reason it is easier for a man to swim in seawater than in fresh or river water. The reason is due to the presence of minerals, salts. The density of seawater is 1.026 gram per centimeter cube, is more than the density of fresh water, which is 1.0 gram per centimeter cube. Therefore, with a smaller portion of the body submerged in seawater, the weight of the water displaced becomes equal to the weight of the body, while weight of the water displaced by equal to the, sorry, I just missed this thing. Therefore, with a smaller portion of the body submerged in seawater, the weight of the water displaced becomes equal to the total weight of the body, while to displace the same weight of fresh or river water, a large portion of the body will have to be submerged in water. So it becomes difficult for the swimmer to in river water. So because in the river water the person is going to sink a bit more than the sea water, so he is going to find it difficult to swim in river water than in sea water. Especially in the Dead Sea, the density of water is 1.16 gram per centimeter cube. Therefore, a man can easily swim in dead water with a small portion submerged inside water so as to balance his weight. So, in Dead Sea, it's very difficult to, in fact, it is very difficult to drown in Dead Sea, because in the Dead Sea, the density of water is 1.16, whereas our body density is 1.07. So, definitely, अगर हम लोग शांति से खड़े रहेंगे तो भी हम लोग डूबेंगे नहीं. Okay. The next is flotation of submarine. A submarine is a fish-shaped watertight boat provided with several ballasts of flotation tanks in its front and rear parts. Figure shows the portion of the submarine to explain its flotation. It is provided with periscope so that the divers can see above the water surface even when the submarine is well inside the water. A submarine can be made to dive into the water or rise up to the surface of the water as and when desired. If a submarine is to dive, the ballast tanks are filled with water so that the average density of the submarine becomes greater than the density of seawater, and the submarine dives into the seawater. It dives into the water. If the submarine is to rise, water from the ballast tank is forced out in the sea by allowing the compressed air to enter the tank. This makes the average density of the submarine less than that of the seawater. As a result, the weight of the water displaced by its partially small submerged part becomes equal to the weight of the submarine, and hence it rises up to the surface of water. So we see over here that how does a submarine work. See, a submarine which is like this. A submarine has got two ballast tanks. There are two ballast tanks over here. Ballast tanks are nothing but the tanks which can take in water. Okay. They say ballast was the one which was used by the ships to keep it loaded. So they put the sand and all, which is nothing but the ballast. So here also, to keep it loaded is the ballast tank. So normally the water will be up to this level. When this particular kind of submarine wants to sink inside, they are going to open the taps over here, open the valves over here, so the water enters into this particular area. So it is entering in this area. So this is completely filled with water. When it completely gets filled in water, this automatically goes down and it rests over here. So that's why this is completely filled with water. That is how the submarine dives into the water. The condition is the next one. When it wants to go up, at that time there is some pipes of compressed air which is over here. So the compressed air is being forced over here, and they open the gates over here so that the water is thrown outside. It will be so much so that the pressure inside over here, the water pressure over here, that will be less than the air pressure. The air pressure will be greater than the water pressure over here, so that the water can pass outside. So the water is made to push outside. So since the water is pushed outside, this becomes empty, and because this becomes empty, hence the weight of the body decreases. When the weight of the body decreases, automatically the displaced liquid is the same, so it is going to go upwards. So accordingly, when the ballasts are the water from the ballast is removed by the compressed air, the submarine starts floating upwards or rises upwards. So this is how the submarine is going to sink, or that is dive inside and come up on the water. Flotation of icebergs. The density of ice is less than density of water. The density of ice is 0.917 gram per centimeter cube, and that of water is 1 gram per centimeter cube. Therefore, huge masses of ice known as icebergs are able to float on water, with major part inside the water surface and only a small portion above the water surface. Now this is the most important part, and that is the reason that Titanic sank. See, the icebergs, when you see from the top, you cannot estimate how big it is at the bottom, because what you see on the top of the surface of the water is only 10% of what is totally which is there downwards. So that's the reason that icebergs are very dangerous, because icebergs का सिर्फ तुम लोग को 10% ऊपर दिखेगा, बाकी का 90% नीचे है, and that shape is not known So it is a possibility that the ship may dash against the iceberg. Of course, nowadays the radar systems and all are very good, and that's why they are able to identify right from the beginning that what will be the size of the iceberg nearby, and it will be easier for them to change the tracks accordingly. So we see that 90% of the iceberg is inside water and only 10% is above water. So volume of the iceberg above the water surface while floating, if the total volume of the iceberg is capital V and the volume of the iceberg submerged in water is small v, then by the principle of flotation we know that the weight of the water displaced by the submerged part is equal to total weight of the iceberg. So V rho G is equal to V rho ice into G. So that's why small v upon big V is equal to rho ice upon rho water. So that's why we have an example is that iceberg rho is 0.917 and water is 1.0 with volume 0.917 V, that is 91.7% of its total volume below the water surface and only 8.3% of its volume above the water surface. Or we can say if the iceberg is 0.917 and the sea water is 1.26, then it is 0.917 upon 1.026, that is 0.893, that is 89.3% of its volume will be inside water and only 10.7% above water. And hence icebergs are dangerous for ships. Icebergs being lighter than water floats on water with their major part nearly 90% inside water and only a small part 10% outside water. Since portion of the iceberg inside the water surface depends upon the density of seawater, therefore for a driver of ship it becomes difficult to estimate the size of the iceberg. Thus an iceberg is very dangerous for the ship as it may collide with the ship and cause damage. Okay, so that was about iceberg. I'll stop here and continue in the next video.